Section 11.6, today we're taking a look at surfaces in space. So last time we looked at lines in space, right? And now we're going to look at surfaces in space. There's two different types of surface we're going to talk about. I don't have a picture of the first one. I should have probably put one in. That would have been nice. It's cylindrical surfaces. So we're going to do one that's very standard, and then we're going to talk about it in general. So consider a standard cylinder from geometry where your base is a circle of radius 5. And this equation, in this dimension, the equation would look like, I don't know why this says 5. One of them should say that they need to match. How about we say radius of 3? We'll make that match there. Just change that to say 3. They're not matching. A radius of 3. So in 3 dimensions, this equation would look like x squared plus y squared equals 9. Everybody good with that? Okay. This is called a right circular cylinder. The picture you should have in mind is like a can of soup. A toilet paper roll, something like that. This Yeti is not perfectly cylindrical, but you have the right idea if you're thinking about that, okay? All right, so consider what the intersection of the surface with the plane z equals k would look like. Since the equation has no z's in it, the intersection with every such plane, which is called the trace of the surface in that plane, is the same, a circle of radius 5. Change that one to a 3 as well. These should all match. I don't know why they're not matching, because I wasn't paying enough attention, I guess. All right, circle of radius 3. So if you were to splice through, we'll take a toilet paper roll for an example, a toilet paper roll, and you can even just think about the cardboard piece in the middle, because it's easier to cut through it and imagine that. So it's hollow, right? It's a surface. It's not a three-dimensional, it's not a solid, it's a surface. And if you were to cut through it horizontally, so that it's cutting through horizontal to like the plane down here that it's sitting on, it would create a circle in its cross-section, right? The cross-section would be a circle. The circle would be the same as the radius 3 of the whole cylinder. So more generally, the cylinder is used to refer to any surface whose traces in every plane, I should say plane, parallel to a given plane are the same. Equations of cylinders will have only 2 variables. So it doesn't have to be a circle. It could be another object. Yes?
Does this remain true if you rotate it 90 degrees? Now the circle isn't flat on an axis?
So it would, but the trace would not be in the trace z, right? It would actually have the third dimension. It would be solid. It would not be centered around one of our axes. So most of the ones we're looking at in this section are all going to be centered around a specific axis.
Okay, so would it be centered around a given plane?
Some other given, not a plane, but a line, another line.
Okay.
Yeah, because this one that we described is in the z, like it's going up the z-axis, if you will, if the z is the vertical axis.
Yeah.
So if you were to tilt it on its side, you'd be going around a different line instead of one of our axis lines.
Diagonally, we have to define some line that hits in that 3. Okay.
Exactly. Yeah. So we're not trying to go too far off kilter here, so we're sticking with our axes, the x, y, and z axis. Yeah, that's a good question. So we're going to see an example of this one where it's not a circle, like a circular cylinder, when we get to our examples. And so I'm just going to wait to show you a picture of that one and how it's still a cylinder when we get there. Our other type of surfaces we're going to look at here are quadric surfaces. So quadric surfaces have this terribly ugly, equation here. It's just a general equation. But it creates 6 different basic types of surfaces, and they all have some features that help us to identify which of them it is, okay? One is called an ellipsoid. So if you can imagine what that might be, you know what an ellipse looks like. And if you 3-dimensionalized it, what object does that sort of similar to in our world?
Football.
Kind of like a football. Okay, it's not a perfect image, but that's the right image to have. An ellipsoid looks kind of like a football. Hyperboloid of 1 sheet and hyperboloid of 2 sheets. We'll see those pictures in a moment. Elliptic cone. So you know what a cone looks like. You see the traffic cones. You see ice cream cones. But they're all circles on the bottom, right? So imagine it was an ellipse on the bottom now, and you made a cone out of it. It's the traffic cone that got squished. Yes? That's your idea. Elliptic paraboloid and hyperbolic. Hyperbolic. I said that right. Hyperbolic paraboloid. And so we're going to look at these 4 others that I haven't sort of described one at a time, and we'll look at the ellipsoid and the elliptic cone as well. All right, so here's our first one, the one that we already described, an ellipsoid. So if you take a look at an ellipsoid, the equation looks a lot like an equation of ellipse, does it not? Yeah, it does. It just looks like you have this sort of third component, z squared over c squared in there. Everything's set equal to 1. If a, b, and c are the same and not 0, then we would actually have a sphere. Okay, so a, b, and c tell you how long and wide and tall it is, and then you've sort of wrapped that all up in, saran wrap or something like that, or paper, so that you can create that spherical or that ellipsoid shape. Okay? Are we good? Oh, not quite. Sorry.
I don't, you can move on. I don't.
So, if A, B, and C equals 0, then it's an ellipsoid?
If an a, b, and c equals 0, then you don't have a shape at all.
Okay, I just wanted
Right?
to
It
make sure that
collapses.
wasn't what I was-
Yeah, it's just talking about a collapsing shape. So it's kind of like when we say something's the denominator can't be 0, right? It's because it doesn't
Okay.
exist.
Yeah,
It's the
yeah.
same idea here. It wouldn't exist. Okay. A hyperboloid of one sheet. Okay, so it's with one sheet because it's all connected. All right, so the picture you're going to see in a minute, they're going to be disconnected pieces. So that's just why it's called one sheet. What is the primary difference between this equation and the previous equation?
Minus D.
There's a subtraction, right? And while it's written on z here, it doesn't have to be the subtraction on z. There's going to be a negative on one of the 3 variables, but it doesn't have to be the z variable. The axis that it is going to be around corresponds to the negative coefficient. So the picture here is the z-axis, the way we normally draw it, because the z-axis is what we draw usually as our vertical axis. But if it were along the x-axis, it would just be laying over on its side, right? Or the y-axis. So if you take one of these images and you flip it over and you lay it down, you're going to have one of the other 2 objects. This is a hyperboloid of one sheet. Good? 2 sheets. So there you go. Disconnected, as expected. So that's why it's called 2 sheets. Let me actually go back to the other picture in a moment because I want to talk about the hyperboloid description here. Before I do, though, notice the difference in the equation. How does this equation differ from the last ones? There's 2 negatives, right? And now the axis will correspond with the variable with the positive coefficient. So my picture here, although it's a general picture, is not the picture for this equation that's written down. At least not the way we normally draw them, right? X is going up and down here in this picture, right? If I want to match my axes to this picture, it's the x-axis now that's my vertical axis. This picture and this picture, although I think it's easier to see it with this one, the reason they're called hyperboloids of one sheet is because there's a hyperbola there. Do you see the hyperbola if I 2-dimensionalize things? Do y'all see it? There's another hyperbola. You can actually see them in here even maybe better because of these cross sections are drawn in a little. You see those hyperbolas all the way around? So we've got hyperbolas in the shape, so hence the phrase or the word hyperboloid inside of our description. Okay, next one, elliptic cone. I already described what this one is. You might notice, though, that it opens upward and it opens downward. That's not how we think of cones usually in terms of our cone-shaped objects in our environment, but they do actually look like this in 3 dimensions. What do you notice is different about this equation than the previous ones? It equals 0, right? It equals 0. And that's actually why we're going to have the point 0, 0, 0, right, the ordered triple, as a part of our graph. That didn't happen on the other ones, correct? Like flip back to any of them you wish, but say this one. The ordered triple 0, 0, 0 is not on this graph. It's inside the hollow space inside of my shape. It can't be on this graph because 0, 0, 0 wouldn't solve this equation, right? Okay, cool. So there's my elliptic cone.
Sorry, will that last one always be at the origin somewhere just to rotate it?
For the ones we're doing, yes.
Yes. Oh,
Yes.
no. Okay.
Yes. For the ones we're doing, yes.
But But it would be the same if like x minus 1.
And we'll do an example of that one where we shift it a little bit, but it won't shift a lot, and we're not going to do many of them. Yeah. Yep. Okay. Elliptic paraboloid. Equation difference.
It equals
Z is
Z.
just chilling.
Ah, okay, it equals z. How is that really different than all of the other ones?
Z is not squared.
Z is not squared. Okay, z is not squared on this one. If you had to describe this shape, what would you describe it to be, physical object-wise?
A cup.
A
like
cup.
Rounded at the bottom.
Yeah, or like a bowl, right? So this looks like something that would sort of hold water, right? But it's not flat enough on the bottom to like sit it down and it not fall over, right? It doesn't have a flat bottom to it.
Greek sounds like a hot pocket.
A hot pocket.
It's not, but
Yeah, it kind of has that imagery of a hot pocket. I like that. Now I'm trying to think what other food objects could you make
To me, it
it?
just looks like the toe box of like a shoe.
It kind of does look like the toe box of a shoe. I was thinking, have you guys seen the plastic oven mitts that you pull stuff out of the oven with? It kind of looks like the hand piece of my plastic. I have a pair at home too, a little bit.
or do you have like those little things that
Especially what you're thinking
for
about.
burning yourself on a coal?
Thing.
Or those little, how would you call it? I don't
I'm
remember.
not
It's like an
sure.
oven mitt for a bowl, basically.
I don't know, I haven't
Put it
seen
in
that.
the-
Oh, I actually know what you're talking
Okay,
about.
You know what else it looks like? It looks like, I have these at home. I haven't used them in forever. My kids would love it if I got them back out and used it. We make frozen popsicles, and they're the molds for
Oh.
frozen popsicles. It looks
Yes.
a lot like this, actually.
Yes.
So,
It could also be a oddly shaped bell.
yeah, there you go.
You were gonna ring it
Like
upside down.
Like it's not a perfect circle. but
Yeah,
it's
like a bell
it's
that
an
you would
ellipse.
ring, but it's an odd shaped one. Yeah.
I said a bill, and I was like,
Yep.
what?
Okay, I think there's one more. This one is perhaps the most interesting in terms of drawing. It's very difficult to draw. This is a hyperbolic paraboloid. So, do you know what this looks like?
Skate park.
Looks kind of like a skate park. Okay, that's a good one.
Saddle.
Looks like a saddle. That's what people usually see. Is it looks like a saddle, like for a horse.
All I see is
on
like
the
a
back
big
camel.
giant ramp
The
thing.
giant ramps on the back of a camel. Yeah.
That'd be a terrifying.
How about the equation? How does it differ from the other ones that we've seen?
So Z is just squared and there's a negative.
Yeah, the z isn't squared and there's a negative, whereas this one had a positive, right? So the positive created this sort of bowl shape, the negative creates this saddle shape. Okay, so here's what we're gonna do. We're gonna draw a little bit.
Uh-oh.
All right, so your drawings do not have to be super accurate in terms of like the dimensional size. They do need to have the right axis that you're extending around. Feel free to switch where the axis is. Like when we talked about, I didn't actually even talk about these axes here. Let me go back and do that real quick. We did on that one, we stopped here. So the elliptic cone, the axis is with the negative coefficient, so that's why it's opening along z here, the negative coefficient. On this one, the axis corresponds to the linear variable, so that again, that's why it's opening along z. Right, this bowl shape is opening upward. And then here, the axis corresponds to the linear variable z, and so the saddle has a saddle shape opening upward, or the skateboard park shape opening upward.
It's just like more difficult.
Okay, so we have not seen one that looks like this at all, so I'm going to just walk you through this one. If you try and take a look at the different options that this looks like, this doesn't look like any of the equations that you actually were given.
Is it not 2D?
It's not two-dimensional. It's three-dimensionalized, but in 2 dimensions, what would it look like? It's a parabola. Okay, so imagine having a parabola, like my circle. This is cylindrical. If I take a circle and I three-dimensionalize it and I just extend it, that creates my cylinder, right? So imagine having my parabola now and three-dimensionalizing it, and it looks an awful lot like this, right?
Hmm.
You're all with me? It's a parabola on the end, but it's sort of a parabola at every cross section.
No,
Three-dimensionalized.
Elliptic cylinder.
You guys are coming up with lovely names. Okay. We do need to figure out where it's three-dimensionalized around, however. So I've got an X and I've got a Y. So in terms of the XY plane, if I were to draw it in 2 dimensions, I could draw it flat in the XY plane. So when I three-dimensionalize it, this is going to be three-dimensionalized up along Z. So my picture's not going to be great. My pictures on none of them are going to be great. But I'm not expecting yours to be either. How's that? That's fair, right?
Suspending disbelief on our homework. Are we-
Suspending disbelief is what you said?
I guess, I don't know.
Okay,
why.
so this would be a parabola laying on its side. And then we're going to extend it upward along the z-axis. So I should label at least my axes. I can do that. So here's z. This one is the x-axis, and this one is the y-axis. That's why it's extending. I don't think I wanted that right. I think I want this one to be y and this one to be x, the way I've already drawn my graph in there.
Yeah.
That'll work. There we go. So we're just switch axes. So you can switch the axes however you wish to make the drawings easier to do. That's fine. And then we're going to take the object that we've drawn, and I'm going to cheat, and I'm going to copy it to be drawn up here. I know it's cheating. And then we're going to connect the lines down. So let's go with dotted lines. That sounds like a good plan. Okay, so it's my piece of paper, right? A piece of paper on its side. Okay, so you're seeing it from this angle like this. That's how I'm drawing it. Like that, opening upward. In particular, when it asks you to describe it, I do want to know what it is we've drawn. So this is, as a general statement, a cylinder. It's a cylinder. Okay, so cylinder doesn't mean it goes all the way around. It means that it's it's a flat surface, right? A two-dimensional surface that you've given height to. So you have to take something that's in two dimensions and you give height to it. And that's what we have here. Okay. You ready to look at another one? So we need to get this into any of the forms that we have seen. All the forms that we've seen have either something set equal to 0 or something set equal to 1 if they have 3 squared terms, which this one does. Right? This has 3 squared terms, and right now it's equal to 9. So how am I going to get this into one of the forms that we've seen in the equations?
Divide it all by 9.
All right, we're going to divide it all by 9. So I've got x squared over 1 plus y squared over 9 plus z squared over 1 equals 1. Okay. What shape do we have? Close. An ellipsoid. Yeah, the closest we have to a sphere. It's an ellipsoid. So that's that football type shape. Which axis is the longest?
Y.
Y. It's going to extend the longest along the y-axis. So I'm going to draw my line in, my axes in. And I'm going to label them as I normally do. So there's x, and there's y, and here's z. And I need it to extend along the y-axis. So this one's not too bad to sort of mark out 3. Why am I using 3? Because 3 squared is 9. Yeah, so I'm going to extend sort of back here, and I'm going to extend my thing back here. And it's going to go up 1, and it's going to go left 1 and right 1 and all of that. And so I'm going to have a football type shape. So I'm going to kind of draw my football type shape in, and then I'm going to try to make it look three-dimensional. So here's my football type shape, or an egg shape. And the way that I make it look three-dimensional is that I give it these sort of, I do it like this in my notes, arches around it. Okay? And if you wanted to do the back side to sort of measure it out, you could do like that.
Oh gosh.
Well, it better look like the y is longer than the x and the z, right? It looks like it's elongated. That seems reasonable to look like that.
You can't really see my 3D lines when you curve it.
Well, when you draw it on your homework, just use a little bit more caution.
Yours looks like a bug.
Okay, you ready for another one?
Oh,
Can I use like different colors somehow?
Sure, you could use different colors. That would be totally fine.
I better be able to use different. I've been doing that the whole time.
Okay, you ready for another one? I think we have 7 total. This is 2.
Just made my bigger.
7?
I think so. That's what I remember doing. Yep, 7.
Wow.
Okay, number 3. It's already in one of the forms. So identify which one is this one.
Hyperboloid.
Of one sheet.
A hyperboloid of one sheet. All right, which axis is it going to extend around?
Z.
Z. Yeah, so each one of them have a different condition, right? It's usually the condition of whichever one's the opposite of the rest. Did you notice that? So sometimes it's positive, sometimes it's negative, but it's the opposite of whichever the ones the majority of the crowd is. So it's Z, so this is going to extend along Z. So we'll draw our axes in. And I need it to look like, okay, so again, to draw it and make it look reasonable, what we're going to do is we're going to draw kind of going to look like a circle through here, except that that's not what I want it to look like. I think I have to draw it by hand. Okay, so I'm going to draw kind of a circular shape. This looks terrible. That's what happens when you have to draw freehand. That wasn't any better. Okay, time to stop trying. I need to copy that same shape and make it bigger. So I'm going to make this shape bigger. I'm just trying to show you guys how you can draw them to make them look kind of reasonable. Copy the same shape, make it bigger.
So, is the radius at the smallest point too?
Oh, I don't know what I just did. Say that again.
So y is over 4. Does that mean that the radius at the smallest point is 2 at the x axis?
So yes, so the 4 is going to be the largest, right? So it's extending 2 along y. So that's why I'm drawing it out this direction. I didn't say that at all. But this is not drawn well, but pretend this is, shift it back a little bit. So there's 2. So you're extending 2 in each direction to draw the shape here. It's an ellipse in this cross section, right? That's why I'm drawing the ellipse shape. So in the xy plane, it's an ellipse. It's going 1 in either direction along x and 2 in either direction along y for the major and the minor axes. And then I'm drawing these larger shapes up here because they're still ellipses above and below, but they get bigger, right? The smallest one, like Alex is pointing out, is in the middle. Okay, so it's terrible. But can you picture it? Those edges are there. It's a big ellipse up here, and then it narrows down to a smaller ellipse around, the XY plane, and then it gets to being larger ellipse as you go down as well. So it extends up and it extends down, creating these ellipse cross sections or ellipse traces.
Can we just connect it with hyperbola on all sides?
Right. That might be a little bit better than I drew the first time. My picture in my notes was much better. See?
Dang.
It's a pretty good one, don't you think? But that's because I'm literally staring at one of these shapes and trying to mimic it. I don't draw well. Okay. All good? Feel free to exaggerate the bigger picture at the bottoms and the top, and it'll make the picture look better if we had exaggerated. So like if I did this one and made it bigger, I think my picture might look better.
It's very wonky.
I'm off screen, but pretend. Oh, there we go. Something like that. All right, next one. Yes? Yes. Y equal x squared plus z squared.
Elliptic paraboloid.
Elliptic paraboloid, yes. How do you know?
Because it matches the equation. We have one not squared, the other two are added together.
Okay, thanks for adding that on the end.
Yep.
Because it matches the equation. Paraboloid, L-O-I-D, paraboloid. Yeah, so we have one variable that's not squared, namely y. The other two variables are squared, so that eliminates it to the last two options that we did, right? There were two of those that had that feature. And then we have positive as opposed to negative, which was our like our saddle shape. So this is an elliptic paraboloid. What do elliptic paraboloids look like?
Like a bowl thing.
It's like a bowl, right? Like this is sort of oddly shaped bowl. And this will be extending along which axis? Y. So I'm going to draw it in the normal X, Y, Z plane that I did, but you're welcome to draw it with the Y facing upward if you would rather.
You just rotate your paper.
Sure. So here's my Z,
Cheating.
What?
X, and Y. So it looks something like this.
Oh, that was perfect. Too easy.
It wasn't too bad, actually, right?
Just make a little parabola.
Some are definitely easier to draw than others. Yeah, so you make a parabola shape, and then you're drawing an ellipse on the end of it.
I don't know
Do you
why.
want-
Mine
I
just,
guess it doesn't matter.
I don't know, there's just something off.
Mine looks like too corny.
All right, we got acorns going on, huh?
Mhm.
Okay, how about number 5?
Like, it just kind of, like, he looks like a circle.
So number 5 doesn't quite look like any of them, but we can manipulate it. What could we manipulate it to do? Square it. So I can have z squared equals x squared plus 4y squared. Then what?
Subtract z.
Okay, so x squared plus 4y squared minus z squared equals 0. And
Sorry.
divide by 4. No, it's on the tip of your tongue. 4. Divide by 4. So we have x squared over 4 plus y squared over 1 plus z squared over 4 equals 0. What shape do I have?
Elliptic cone.
Yep, it is an elliptic cone. Which axis am I opening around?
Y.
Z. It's the one that's
Should be a
off. Oh,
negative.
I have a typo. Yeah, how about that then? Better?
Z.
Z. Yeah, it's around Z. There is one other thing that we need to take into consideration. How did the equation start?
Square root.
As a square root.
So it can't extend the other way.
Right. This will only open upward. Because from here at the very beginning, remember this is called a principal square root. It's the understood positive part of this. This will only be for the z values that are greater than or equal to 0. So I have sort of the stereotypical ice cream cone now. I only have half of it, right? So as I'm drawing this, I'm going to open upward on my cone shape. And it's going to have an ellipse shape on top, not a circle. But there's really not a way for it to look more elliptical or more circular in this three-dimensional way that we're drawing very much. So that works just fine. X, Y, and Z. And of course, taking careful note that the only reason that we're not drawing the bottom half is because the problem didn't start out with Z being squared, right? That's something we introduced in the process.
But if it was, we would have just done the same thing upside down.
Yep, we would have. You're right. Okay. Number 6.
This is. Hyperbolic. Hyperbolic parabola?
It is a hyperbolic paraboloid. It's not quite in the right form to be able to work with it right now, as is. But what I need to do.
Then I'm gonna subtract x and add the y's over to the other side.
Yep. Okay, so we've subtracted or removed, right? We've moved the other pieces to the other side. The z is left alone. And so this actually tells us that we are opening along the z-axis. it's the odd man out, right? Oh, so let me write down what you just told me it was. It's a hyperbolic paraboloid. And here's my axis. Okay, I have a really difficult time drawing this one, so let's see how well I can do today. Not with the line, I'm not going to do it at all. It's looking really good. At least
So-
for me.
The 4y, does that mean it extends out 2, or is that 4? Actually 4 on the y.
So we're drawing parabolas on the end, right? You see my
Yes.
parabola there?
Yes.
Okay, so if I took off my shading stuff I was trying to do, you see the parabola, and so the parabola is opening downward. In the z direction, it's opening up. Let's see if we can draw it back from over
Wouldn't
here.
it be the,
Did we need to divide by 4 to put that 4 on the bottom, or would that mess it up? Because then it's.
Well, it'd be 1/4. It would be 1/4 on the bottom, because I don't want the z to have a number over there. So if I were to truly put it into all of the correct form, the way we saw it, it would look like this.
So our b for b squared underneath is 1/2.
Yeah,
Okay.
yes, so it'd be 1/2. Okay, so here's my original picture. This is the x and the y.
so x is positive in that one.
X is
so it
positive in
goes
that
to
one,
x.
so it's opening sort of
Rotating it
long
90
ways around
degrees.
x, and then it's opening, ours is opening around y, yeah.
Okay. So
So if you
does
take
there-
it and to rotate it.
So
Does
we
it just go infinitely high as you
Yes,
extend out?
it does.
So how do you know, like, the width to what to do with the
You
1/2?
can't, there's no way to draw it accurately. I mean, like, we're not gonna be able to get that accurate.
Okay.
Yeah, so we're not gonna try to deal with the fact that there's a 1/2 dealing that, like you guys can have noticed there or not. That's not too bad. You can picture the saddle. It's all right? Okay, good deal. You got one more. I can't draw that one very well. Okay. How about this one?
Wait, we go back.
Yep.
I'm good.
Is the hyperboloid of 2 sheets?
Yeah, it's the only one we have left, right?
Yeah.
It is. Let's get it into a form that it actually looks like it, though. So what would I need to do?
Divide by 9.
Okay, so we're going to divide everything by 9, and I'm going to put the positive term at the beginning because that's kind of how they show up in their equations. So this should say z squared over 1 minus x squared over, not x cubed, good grief, x squared over 9 minus y squared over 9 equals 1. Okay, so just like you mentioned, it is a hyperboloid of 2 sheets. What is the axis it's extending around? It is the, so I'm going to flip back just so you can see this one because it's also kind of a weird one to draw. So it kind of looks like, we didn't really talk about this one, but it kind of looks like a flying saucer. Opening up, there's one in the bottom too. But that's kind of like a bowl shape, right? And you can see that there's these ellipses, right? If you just go around it, that they taper down and then they don't exist for a period of time in between, and then they pick up below. And we didn't draw it either, but do you see the hyperboloids, the hyperbolas in there? You see those shapes? And you see the ellipses going around, right? You can't really see that, but they're going around the shape in the back.
Are they ellipses or circles?
It depends on what the equations are. So if the A's and the B's and the C's, if they match in a certain way, then they would be circles. But in general, they would be ellipses.
All right,
Yeah.
'cause the picture looks very circular.
Yeah, it does. And it's hard to not draw it so that it looks that way, and that's probably part of why it looks that way anyway. So our shape is opening around the z-axis. So here's my z, x, and y, and we're have these sort of bowl shape. And oh my goodness, it's maybe worse than the last one I did. Okay. There's space in between them. I mean, like that's the space in between. They don't have to be that far apart drawn, but I was trying to get them to show that they're not connected.
It's like 2 pies.
2 pies, I like that. I don't know what I did there. I think that was me trying to connect things nicely. All right, so yeah, kind of like a pie tin above and a pie tin below. And they don't really look flat on the bottom quite like I've drawn them. They do look more pointed shaped if you look back at the picture on there too. So. Let me make a comment before I end this. If you look at the directions at the bottom for the problems that you're going to be taking a look at, it looks like there's quite a few of them. That 5 through 10, I'm pretty sure if I remember right that they're either matching or something like that. So it's not like you're drawing them from scratch. So it looks like there's a lot of pictures you're going to draw, but I don't think you're drawing for all of them. So just pay attention to the directions when you're looking at those, okay?